In this question we're going to do potential flow theory. So we've got ourselves two types of flows. We've got a vortex flow, and that's given by a given velocity profile. So we've got ourselves u1, so that's the velocity in the x direction, which is given by z divided by x squared plus z squared. So we're looking at a two-dimensional space in the z x plane, and then we've got w1 is going to be equal to minus x divided by x squared plus z squared. Now we've got also a uniform flow, and that's given by two different velocities. It's going to be given by u2, well, it's a uniform flow in the x direction, so u2 is going to be equal to v infinity, and then we've got a w2 which is equal to 0. Okay, what we want to do now is superimpose these two flows and determine the pressure field and the location of the point at which the maximum pressure occurs. Right? So we want to know P, and we want to know P max. Those are the two things that we're after. Right. In order to first get the flow and get the velocity field of the flow, because now we've got the velocity fields of the two individual flows, but if you combine them together, you can't just superpose the velocity fields together. However, we know that there is a relation between the velocity field and the stream functions. And we know that the stream functions are a solution to the Laplace equation, and they can be superposed together. So you can sum them. So if we now find the psi for the vortex flow, and we find psi for the uniform flow, then we can add them together, and then we can get the velocity field. And once we've got the velocity field, we're going to use the Bernoulli equation to get the pressure field. Okay, so that's going to be our strategic plan. So we first need to get those psi's. So what we can do is actually express d psi. So a variation of my first, this is the vortex one. So for psi vortex, it's going to be a variation, and we'll call that psi 1 from now on. So psi vortex is equal to psi 1, that's less writing. And this is going to be psi 2. So this is going to be psi 1 dz plus psi 1 dx. So it's going to be a function of x and z. So we need those two contributions. Now we know that there is a relation, that's the definition of psi, that the velocity in x direction is defined as d psi dz, and for w we have minus d psi 1 dx. So by definition you've got these two relations. So we can use those into that equation for d psi 1. So we can now write d psi 1 as u1 dz minus w1 dx. Right, so if we want to solve this, it's, we see ourselves having an x squared and a z squared, so to transform in polar coordinates will probably give me something nice. So we're going to do that. So we first need to know what my dz and dx are in this expression for the psi 1. So z is given by r sinus theta, And x is given by r cosinus theta. If we know these, then we know that dz is given as dz, d theta, plus dz, dr. So if we evaluate dz d theta, well, the derivative of that r times sinus theta to theta will give me r times the cosinus of theta, d theta. And the second term is the derivative to r. Well, it's linear in r, so this is going to give me a sinus theta. Great. So we can do the same thing for x. So we've got dx is dx d theta times d theta plus dx dr times dr. So what does that give me? Well, we first take the derivative of that cosinus that we've got there, and we get a minus sinus. So we minus r times the sinus of theta, and we multiply that times d theta. And then we add the derivative to r, which is, x is linear in r here. So we take the derivative of that thing, and we get cosinus theta, and we multiply that times dr, plus cosinus of theta times dr. There we go. So we've got these two expressions. Now, we've got those in polar coordinates. Now we need to get u1 and w1 in polar coordinates. So we can get that by substituting our expressions for x and z on this line right here. And we substitute that into our definitions that were in the question right here. So if we do that, we're going to get u1 is going to be r times sinus theta divided by r squared cosinus squared theta plus r squared sinus squared theta. And we see that we've got a cosinus squared plus a sinus squared there at the bottom. So that's going to be 1 if I add them up. So we get r squared times 1. So we get r squared at the bottom. We have r sinus theta divided by r squared. So this is, in the end, going to give me sinus theta divided by r. So it reduces to something fairly simple. Then we've got for w1, we can do exactly the same trick. So we've got r times the cosinus of theta. We've got a minus sign in front of the entire equation. And at the bottom, we've got exactly the same cosinus squared theta plus r squared sinus squared theta. Right, and so this will reduce to cosinus of theta, and we divide that by r. Now we've got all the ingredients that we need to evaluate what d psi 1 is. So d psi 1 is going to be equal to sinus theta divided by r. So this is u1. We multiply that u1 by dz, and dz was defined as r times the cosinus of theta, d theta, plus sinus of theta, dr. And then we add, so we'll continue in the next line, we'll add cosinus theta divided by r. And we multiply that times minus theta d theta plus cosinus theta dr. like that. Okay, I would like to highlight the fact that if you go back to the previous page, then you see that there is a minus sign in this equation here. There's a minus sign here. And also there is a minus sign here in this equation. Right, so if those two equations are evaluated, we're going to cancel out the minus sign. Okay, so that's important. So that gives you this plus sign here. So that's something to realize. Right, so let's evaluate the individual terms. So we're going to get that d psi theta is sinus theta cosinus theta d theta. You see that the r's have cancelled out. Then we've got the second term is going to be sinus squared, so plus sinus squared theta divided by r and multiplied times dr. Then we've got ourselves a term which is a minus the cosinus, again the r's cancel out in this term, so cosinus theta sinus theta, and we multiply that times d theta. There we go. And then we've got another term, so this is plus, and then I'll go back to the next line again. We've got a cosinus, so let's write it here, cosinus theta squared divided by r dr. Okay? So again, we see a sinus squared right here, and we see a cosinus squared right here. So we can merge those two. And actually the other two terms are going to cancel out because they're identical except for this minus sign here. So what we're left with is going to be a 1 divided by r sinus squared theta plus cosinus squared theta dr, which is going to be 1 over r dr. Great, so that's d psi 1. So if we want to evaluate what d psi 1 is, we're going to get psi 1 is going to be that integral over 1 over r. And we can evaluate that. That's the natural logarithm of r. And we sort of knew this because we know by definition that d psi vortex, so from the theory we've learned, we know that psi vortex, if we look that up in standard tables, is the natural logarithm of r divided by 2 pi. So what we basically say is, now suppose that gamma is 2 pi in strength. That's the circulation. Then we're going to get exactly the result that we derive now from the velocity fields. Okay, so now this was only the first flow field. Second flow field is a bit easier though. So we know that there is a relation by definition again. So U2 is by definition d psi 2 dz. So the velocity field in x direction is the derivative of the stream function to z. So from that it follows that psi 2 can be evaluated if we integrate u2 across dz. Now u2 is a constant, it's v infinity, so this is an easy integral. That's going to be v infinity times z. And v infinity times z, again, in polar coordinates, is going to be v infinity times r times the sinus of theta. So that was quick. That was an easy one. So now we've got this result here, and we've got this result here. So we can add both of them now. So we've got a psi total, and that's the point where we can actually superimpose the vortex stream function and the uniform flow stream function, and that's just adding it up. So it's psi1 plus psi2. So if we do that, we're going to get the natural logarithm of r plus v infinity times r times the sinus of theta. Now great, so we've got ourselves a stream function. Now we need to get our radial and circumferential velocity. So we're talking about a vortex flow, so typically the polar coordinates are the way to go for this kind of flow. So again, we can go to the definitions for u theta. U theta is defined as the derivative of the stream function. In this case, this is going to be psi total dr. So we take the derivative of that thing to r, and what we're going to get is minus 1 over r minus v infinity times the sinus of theta. We can do the same thing for the radial velocity. So ur is, by definition, 1 divided by r, the derivative of the total stream function to theta. And this is going to be equal to v infinity times the cosinus of theta. So you see that the ln of r term vanishes because it's not a function of theta. Okay, so now we've got u theta, we've got ur. Now we're going to the pressure field, and we know that Bernoulli's equation can do that for potential flows. So we've got ourselves a P infinity plus a half rho infinity V infinity squared. Must be on the same streamline as some point near the vortex, which is going to be defined as P plus a half, density is not changing because we're considering potential flow, an incompressible flow therefore, so rho is going to be constant, times the V that we're finding at that point squared. Now that V here at the end is going to be defined by my u theta and ur. So V squared is going to be equal to u theta squared plus the contribution of the radial components squared. Good, so we need to evaluate what that is. And we can because we've got an expression for both of them. So that's the next thing we'll do. We've got ourselves a v squared is going to be equal to 1 divided by r squared. So that's the first term. Then we've got a v infinity squared sinus squared theta. Then we've got ourselves a plus 2v infinity sinus theta divided by r. So this was all equal to u theta squared. So all of this is u theta squared. And then we've got another term plus v infinity squared cosinus squared theta. And that thing is my ur squared. Great, so we've got that, and we need to substitute that into the Bernoulli equation. So we rearrange the equation a bit, and we'll get p minus p infinity. Throw the pressures to the left-hand side and all the other velocity terms to the right-hand side. We're going to get half rho infinity v infinity squared, and then all the terms from that u theta and ur are going to come in. So that's minus, what is it, half rho infinity 1 divided by r squared. Then we've got minus, and what you see is that here and here we've got ourselves a sinus squared plus a cosinus squared, which is going to give me 1. So that's going to result then in a term which is a half rho infinity v infinity squared. Then we've got a final term, which is my v infinity times rho infinity times the sinus of theta, and we divide all that times r. You see that the 2 has vanished because there's multiplied times a half. Okay? So now again we see, if we look at this equation, that we've got these two terms and they cancel out against each other. So what is my final result? My final result is going to be minus rho infinity divided by 2r squared minus v infinity rho infinity sinus theta divided by r. Right. And that's my pressure field in the end. Right, so the next thing was to find the maximum pressure within that field. So how do we find a maximum, or how do we find a minimum? By taking the derivative. So we need to take the derivative of the pressure to theta and to r. Okay, so we've got ourselves dp d theta is going to be the derivative of that equation that we found to theta. Well, there's only a sinus theta in there, so this is going to give me a cosinus times the cosinus of theta divided by r. So that's quite easy, and that derivative must be equal to 0. If that's the case, well, a cosinus of theta is 0 if theta is plus or minus a half pi. So theta is equal to plus minus pi over 2. So it could be a point that has theta plus or theta minus pi over 2. We don't know yet what r is going to be, but we need to get all our derivatives, so also the derivative to r must be equal to 0. So dp dr can be evaluated. If we do that, then we've got a r to the power of minus 2. So that's going to give minus 2 times r to the power of minus 3. So this is going to be rho times divided by r to the power of 3. And we add to that the derivative of r to the power of minus 1. So that is minus r to the power of minus 2. So now we've got v infinity rho infinity sinus of theta divided by r squared. So you see that both those minus signs have vanished because we had an r below the divider. And that must be equal to 0. So we need to solve for that equation. So we can pre-multiply times r squared on both sides, and we can get rid of the rho's. So if we can get rid of rho, we're going to get 1 divided by r from the first term, which must be equal to minus v infinity times the sinus of theta. And that's not divided by r squared because we multiplied the entire equation times r squared. So that's my relation. Okay, so from that it follows that r is equal to minus 1 divided by v infinity sinus of theta. So there's a relation between r and theta at which that minimum occurs or maximum occurs. Right, so we know the values for theta, so we can go two ways. It's either plus or minus pi over 2. So we go in that direction. We've got theta is equal to pi divided by 2. If we substitute that in our equation, we're going to get an expression for r. R is actually going to be minus 1 divided by v infinity. The other alternative is theta is equal to minus pi over 2. And if we do that, we're going to get R is equal to 1 divided by V infinity. Now, V infinity is a positive number. So if V infinity is positive, then what I'm getting here is a negative value for R, and R is the polar coordinate in radial direction. So the radial direction is always, by definition, going to be positive. So this is an invalid result. So my final result is going to be that one. That's going to be my correct solution. So my P max is defined as my P evaluated at 1 divided by V infinity and minus pi over 2. So that's the R and theta value at which this occurs. And this happens to be a stagnation point. So if you substitute those back into the original equations for u theta and u r that we derived a bit before, then you'll see that you're going to get u theta is equal to 0 and u r is going to be equal to 0. And that makes perfect sense based on the Bernoulli equation, that your stagnation point is actually your maximum pressure. So that was this exercise.